Ever since the dawn of science, or even when science was still considered a part of philosophy, humanity has pondered one question: what is the ultimate meaning of the universe? Today, let's explore how much of the essence of everything still remains a mystery, waiting for us to unveil. A few centuries ago, when science was still in its infancy, people were often bewildered by many common phenomena. The ancients struggled to understand lightning, stars, diseases, magnetism, and even ourselves. The world seemed filled with mystical elements, powerful forces, and strange creatures that went beyond human understanding. Fast forward to today, and it's rare for us to encounter unexplained phenomena in daily life. Whether it's lightning, stars, diseases, or magnetism, we recognize that natural laws govern them. While awe-inspiring, these things are bound by the laws of physics. Indeed, our sense of wonder at encountering the inexplicable has become so treasured that we willingly pay to relive such experiences, as evidenced by the allure of magic shows. Beyond understanding, we have also gained control over our surroundings. We can make 400-ton airplanes fly across oceans, control quantum mechanical effects in billions of transistors on a chip, and even carry out organ transplants. In a sense, we live in an age of wonders. We excel in understanding both the macroscopic and microscopic aspects of the real world. But does that mean we know it all? Are our theories comprehensive enough to explain everything? Clearly not. As you've gleaned from our discussions, dark matter and dark energy, ubiquitous yet mysterious components of the universe, are largely unknown. Our mastery is confined to a tiny corner of the universe. The cosmos is still enveloped in a vast sea of unknowns. Despite our understanding of the world around us, we remain largely ignorant about the universe. How far are we from discovering the theory of everything, which captures the essence of all things? Does such a theory even exist? Can it unravel all the mysteries of the universe? The essence of all things, at its core, is a deeply succinct and mathematical description of space-time, all matter, energy, and forces in the universe. Let's dissect this definition. It must encompass matter, as the theory should describe every entity that makes up the universe. It should also cover forces, as we want to understand not just inert clumps of matter but how they interact. More importantly, this theory needs to be as simple and profound as possible, capturing the most fundamental and reasonable description of the universe. It should use the fewest variables and undefined constants while still being able to describe the entire universe on the smallest scales. We aim to find the most basic building blocks and understand their fundamental interactions. Imagine a universe composed of nested layers, like an onion. For example, atoms are made up of a nucleus consisting of protons and neutrons, surrounded by orbiting electrons. You've probably seen similar models with a central circle surrounded by smaller orbs. This widely accepted scientific model is remarkable not just because it's famous but because it hints at a deeper truth: matter might be composed of smaller pieces. In economic studies, the collective behavior can be described without analyzing the psychology of every individual. Likewise, in physics, we have various theories that work well at different scales. Before we understood DNA, we had the theory of evolution. Before we discovered the Higgs boson and quarks, we had already sent men to the moon. So, is there a smallest unit of length in the universe? If the real world were like pixels on a screen, what would that entail? If there's no smallest unit, then a more fundamental theory might forever elude us. Are electrons, quarks, and other particles truly the most basic components? What about the forces acting between them? Is there a fundamental theory that could encompass all these forces? We've raised many questions that invite further discussion and exploration. Let's begin with the first intriguing question. Is there a minimum unit of length, or a smallest resolution, in our universe? In other words, is our reality pixelated? It's a captivating thought to consider that our world might be like a digital image made of tiny, indivisible units. Quantum mechanics tells us that we can't pinpoint the exact position of a particle due to the inherent randomness in quantum systems. Yet, it also suggests that beyond a certain scale, position information simply ceases to exist, indicating that the universe could indeed have a smallest meaningful pixel of length. But how small are these hypothetical pixels? That's still unclear. Physicists have made rough estimates of this minimum length by combining key universal constants like Planck's constant, h, the speed of light, and the gravitational constant, resulting in the Planck length, a number so small it has 35 zeros after the decimal point. Although this isn't rigorously derived, each of these constants represents important physical quantities in the quantum realm, and together they could provide clues about the universe's fundamental scale. But can we verify this? Not yet. The tools we use to probe tiny distances have advanced from optical microscopes operating at the visible light wavelength range to electron microscopes and high-energy particle colliders. Electron microscopes can detect matter at scales of around 10 to the power of -10 meters, while particle colliders can delve into the internal structures of protons at about 10 to the power of -20 meters. But this is still far from the scale needed to verify the reality of the Planck length, off by about 15 orders of magnitude, which means we might be missing a plethora of information. This daunting gap leaves us humbled. Although there's no conclusive proof that the universe is pixelated, both quantum mechanics and our current understanding of universal constants strongly hint at the possibility of a smallest unit of length, albeit an incredibly tiny one. After discussing the concept of a minimal length, let's move on to the second question. What is the most fundamental particle? Is it the electrons, quarks, or something else we've discovered? Likely not. Electrons and quarks seem more like conglomerates of smaller, even more fundamental particles. To figure out if electrons and quarks are composite particles made of smaller units, we'd need to keep increasing the collision energies between particles. Any composite particle should be held together by some form of binding energy. For example, a hydrogen atom is essentially a proton and an electron bound by electromagnetic forces, and a proton is made of 3 quarks held together by the strong nuclear force. If energy applied to a composite particle is below its internal binding energy, it behaves as if it's a solid entity. However, if the energy surpasses that binding energy, the particle disintegrates, revealing its more basic components. Although it's uncertain whether electrons and quarks are made up of smaller units, even if they are, we don't know how much energy would be required to break them apart. As of now, our colliders are insufficient for finding particles smaller than electrons and quarks. Another approach is to look for patterns in the periodic table of fundamental particles and search for new particles that might fill in the gaps. Discovering more particles similar to electrons and quarks might help us deduce some pattern in the table and potentially uncover clues to deeper structures. Much like how early research on the element periodic table did, this approach could reveal whether there's more to known particles than meets the eye. Lastly, the final piece of the puzzle in understanding the fabric of everything revolves around a description of fundamental forces in the universe. How many fundamental forces should there be, and could they possibly be different aspects of the same phenomenon? Understanding these forces boils down to understanding the nature of the forces we already know. For example, if you asked ancient people about the kinds of forces that exist, they would list many: gravity, push, breakage, pressure, friction, and so on. However, as scientists gained more insights, it became clear that many of these forces were interconnected. These arrangements and patterns hinted at some underlying unity among them. Just as the element periodic table gave insights into combinations of electrons, protons, and neutrons, similar thinking could apply to the particles and forces at play here. Although many mysteries remain, the clues are right before us. We know that when a tree branch comes into contact with an elephant, the forces they exert on each other are fundamentally due to the repulsion between atoms. The unified theory of electromagnetism didn't emerge until the 19th century. Earlier, we spoke about James Clerk Maxwell, who discovered that electric currents generate magnetic fields, and moving magnets can generate electric currents. He summarized all the known electromagnetic equations at that time, including Ampere's law, Faraday's law, and Gauss's law. Maxwell realized that these laws show perfect symmetry, implying that electricity and magnetism could be described as different facets of the same underlying concept. In recent years, a similar unification has occurred between the weak nuclear force and electromagnetism. These seemingly distinct forces turn out to be manifestations of the same fundamental force, dubbed the electroweak force. Furthermore, the familiar photon is just the tip of the iceberg. This force can also give rise to W and Z bosons, which are the carriers of the weak nuclear force. We've now reduced our list of fundamental forces to three: the electroweak force with its corresponding particles, photons, W bosons, and Z bosons; the strong nuclear force with gluons; and gravity, carried by the hypothetical graviton. Can we take this reduction a step further? Is it possible that all these forces could be manifestations of a single force? The answer remains unknown. For any such unified theory to describe everything in the cosmos most simply and fundamentally, it would have to account for the universe at its smallest scales. This requires that the theory describe the tiniest volumes in the universe. This theory would also have to provide a unified description of all basic interactions, or forces. While we do have some clues and theories about the smallest scales, our understanding is still limited. We have identified 12 fundamental particles, which as of now, cannot be broken down further. We have also outlined their interactions through the electroweak force, strong nuclear force, and gravity. Yet, how far we are from a complete physical theory is still unknown. Despite the uncertainty, we continue to speculate. Current trends suggest that we might eventually arrive at a unified theory that describes matter, forces, and space in the universe. This theory could reveal the universe's smallest units or prove that such units don't exist. With such a theory, we might be able to delve into every layer of the universe, explaining all phenomena with a single particle and a single force. While we seem to be making progress, it's crucial to remember that our current theories only account for about 5% of the universe. As mentioned earlier, we don't know how to account for the remaining 95%. One puzzling issue in constructing a theory of everything is how to reconcile gravity with quantum mechanics, a significant obstacle in our quest for a complete theory. We will explore this problem further. Earlier, we talked about the two major theoretical frameworks of the universe: quantum mechanics and general relativity. Quantum mechanics posits that everything in the universe, including forces, consists of quantum particles. These quantum particles are tiny fluctuations with inherent uncertainties due to their wave-like nature. These fluctuations interact across various scales of the universe, exchanging wave-like particles. While quantum theories for the strong nuclear force and the electroweak force exist, a quantum theory for gravity does not. On the other hand, general relativity is a classical theory that predates quantum mechanics. It doesn't quantumize the universe and doesn't consider matter and information to be quantized. However, it is adept at modeling gravity, calculating its effects. According to general relativity, gravity isn't a force but rather a curvature of spacetime itself. When an object has mass, it warps the spacetime around it, causing nearby objects to curve towards it. Thus, we have two great theories: quantum mechanics, which explains most of the fundamental forces, and general relativity, which explains gravity. However, they are currently incompatible. This incompatibility isn't for lack of trying. When physicists attempt to marry quantum mechanics and general relativity, two primary issues arise. First, quantum mechanics seems only to work in flat, uncurved spaces. When applied to curved space for gravity, oddities appear. To make quantum mechanics meaningful, physicists use a mathematical trick known as renormalization. However, when applied to quantum gravity in curved space, it fails. Simply put, this involves deep mathematical problems that cannot be fully discussed here. In other words, whenever we try to apply current quantum gravity theories, we get an infinite number of issues that make calculations nonsensical. This might be because gravity has some feedback effect. The more space bends, the stronger the gravity, and the greater the mass it attracts. This feedback effect is nonlinear, which is not the case in quantum descriptions of the electroweak and strong nuclear forces that exist in flat spaces. While this might sound dizzying, it illustrates that deeper physics often requires appropriate mathematical foundations for full comprehension. To sum it up, Merging these two theories has proven difficult due to mathematical complexities and philosophical differences in their descriptions of gravity. While we've begun to grasp the technology to potentially detect gravity particles, experimental evidence remains elusive. As a result, these two theories describing the workings of the universe are hard to reconcile. We're not even sure if they can be. Our current quantum gravity theories consistently produce irrational predictions. Perhaps we haven't found the right mathematical tools to unify these theories, or perhaps our method of unification is flawed, or both. Though we know how to compute forces in quantum mechanics, we don't know how to apply this in curved space scenarios. How do we determine whether a significant scientific breakthrough has been made? Imagine that scientists have successfully constructed a particle accelerator as large as the solar system and, using this device, have deduced the Planck length, the smallest meaningful unit of distance for material reality. Suppose we could master these fundamental units and explain their interactions, thereby extrapolating to larger-scale natural phenomena. But does this mean we've made a substantial achievement? You might be familiar with Occam's Razor, which posits that, given two theories explaining the same phenomenon, the simpler one is more likely to be correct. Physicists often find deep connections between different phenomena, streamlining theories in the process. This may explain why physicists sometimes look down on other disciplines. Could there be a single, simplest theory, just as we search for the smallest particle? While we might prove that the smallest distance or particle exists, can we prove that there's a simplest theory for everything? How do we know when we've reached this monumental milestone? Consider this scenario. You've developed a theory that explains everything and incorporates a specific number, irrespective of its value, which is crucial. Let's assume this number represents the mass of a fundamental particle, a neutrino. To apply the theory, one must know this exact value. So, you might think of using the newly built Colossal Collider to measure the neutrino's mass and plug it into your theory. Now, another person comes along with a slightly different theory that also explains everything. However, their theory derives the exact mass of the neutrino from its equations, no measurement needed. In this case, their theory has one fewer arbitrary variable than yours. Even if your equation looks simpler, their equation provides more information about the universe. This is because their equation explains why the neutrino's mass must be a particular value, while yours only specifies its mass based on experimental measurements, leaving the underlying reason a mystery. Hence, their theory is more fundamental and simpler, using fewer numbers. This example aims to show how we might judge if we found a theory of everything. One way could be to count the number of arbitrary numbers in a theory. The fewer, the closer we are to the essence of the universe. Perhaps this core doesn't contain any numbers at all, and the universe is fundamentally some elegant mathematical form. All known constants, like the gravitational constant or the Planck length, could be derived from the theory rather than measured. Currently, the Standard Model of Particle Physics, our most comprehensive model, includes a plethora of parameters: 12 for quark and lepton masses, 4 for quark mixing, and 3 for the strengths of the weak and strong forces, plus 2 more in the Higgs field theory. That's a total of 21 numbers, and this doesn't even include gravity, dark matter, or dark energy. We can use these numbers but have no idea why they are what they are. In fact, we don't know how to judge whether a theory truly encompasses everything, or whether the numbers in the universe are random. If we one day find a theory with just one number, say, 4, we'd still have to ask, why 4? Could this fundamental number have been randomly set in the early universe? Different numbers might exist in other universes. While intriguing, most of these ideas veer into philosophical territory rather than staying within empirically testable scientific hypotheses. Given that we are 15 orders of magnitude away from measuring the Planck length, perhaps we should try another approach. Instead of peeling the onion, layer by layer, why not start from the core? Starting from the core means we don't probe from 10 to the power of -20 to 10 to the power of -21 or look for levels smaller than quarks. We assume there is an absolutely fundamental unit far smaller than a quark, around 10 to the power of -15. If your theory can explain phenomena we observe today, then it is technically valid. There are several such core-first theories, the most famous being string theory, which suggests the universe could have up to 10 or even 11 dimensions, or possibly more. In summary, the quest for a theory of everything is intricate and multifaceted. The closest we might come to understanding the universe's true nature may not lie in the amount of data we can collect, but rather in the elegance and simplicity of the equations we formulate. The fewer arbitrary numbers, the closer we might be to revealing the universe's underlying elegance and simplicity. So, what about these extra dimensions? They might be curled up or tiny, making them unobservable to us. These dimensions are filled with tiny strings that vibrate in various ways to produce different kinds of particles. We've already discovered many such particles, and the theory even suggests particles that we haven't yet found, like gravitons. What's more exciting is that string theory is often heralded for its mathematical and theoretical elegance. Essentially, it's a theory that aims to unify all forces and describe the universe at its most fundamental level. However, there are several significant issues with string theory. Firstly, although it aspires to describe the entire universe, it's still a work in progress with its mathematical methods continually being refined. Some hurdles need to be cleared before it can be regarded as a complete descriptive theory. Secondly, string theory, as it stands, doesn't offer testable predictions. For any theory to claim it has found the universe's most fundamental building blocks, whether particles or vibrating strings, it must provide verifiable predictions. Because string theory currently operates at the Planck length scale, we can't test it yet as our methods haven't reached that level of precision. Therefore, believing in string theory at this point is a matter of philosophy, mathematics, or even faith, rather than physics. However, someday, advances in experimental technology and insights from physicists might find universe characteristics that align with string theory predictions, validating it. That said, this has yet to become a reality. Another challenge string theory faces is the landscape problem. The dynamics it predicts are determined by the number and shape of spacetime dimensions, and there are myriad ways these dimensions can be arranged, estimated to be around 10 to the power of 500 possibilities. This number is overwhelmingly large. While further development in string theory might narrow down these choices, there's a long way to go. So, for now, string theory is mathematically elegant and perhaps the best option we have, but anyone claiming it to be the final explanation for everything in the universe should be met with skepticism. Moving on, let's talk about emergence. What is an emergent phenomenon? To clarify, consider this analogy. Imagine our TV screen is made up of countless tiny pixels. Without delving into the technological specifics, assume each pixel is a tiny light bulb. Suppose we have precise formulas predicting whether each light will emit red, yellow, or blue light at any given time. While these formulas can accurately predict the state of each light at the micro level, they cannot tell us what TV show is currently on. To understand what's playing, one simply needs to step back and see whether it's the news, weather forecast, etc. This shift from micro to macro phenomena is what we call emergence, a significant feature of the physical world. For instance, when describing the motion of a bouncing ball, Newtonian mechanics from high school suffices. We treat the ball as a single object subject to forces, sketch a simple parabola, and encapsulate the situation in a straightforward mathematical equation. Alternatively, you could use quantum field theory to describe the 10 to the power of 25 particles that make up the ball and their interactions at a quantum level. While theoretically accurate, this approach would be computationally infeasible. If a correct theory of fundamental reality exists, it could theoretically provide us with insights on everything from galaxy formation to fluid dynamics to organic chemistry. But this is practically impossible, and science doesn't work this way. No one expects a surfer to understand string theory to calculate how many particles help him stand on his surfboard. Nor do we expect recipes to be written in terms of quarks and electrons. If early scientists had to start their inquiry from fundamental particles, we'd have made little progress. The search for a theory of everything is more a physicist's obsession. Humanity strives to understand the deepest, most basic truths of the universe, not to dictate cooking methods or any other practical action, but to satisfy our curiosity about the why. In earlier discussions, we mentioned various challenges to finding the ultimate theory, but these aren't sufficient to halt our explorations. Each time we peel back a layer of reality, each time we step closer to the core of the universe, we uncover astonishing structures. These revelations could profoundly change our understanding of our very existence, and perhaps that's what distinguishes us humans from other forms of life.